In the series of discussing the particular gate 2026 syllabus, now we are ahead, right? So we have done till this particular programming and data structures part, right? Now we'll actually have a look at the other sections which are on there for the gate 2026. So you have the algorithms, right, which is pretty famous topic of the gate 2026, right? Or it's again any other previous examinations, right? So what the topics which they have mentioned into this are searching, sorting, hashing, asymptotic worst case time complexity and space complexity, algorithm design techniques, greedy, dynamic programming, divide and conquer, graph traversal, minimum spanning trees, and shortest paths. So let's usually list down the topics which are very commonly asked in these particular questions. One is actually this worst case asymptotic analysis, right? So what happens is that in this they actually give a particular function, right? And they might actually ask you to find the time complexity, right? There's a very nice book which I have seen for this particular thing. Is actually by Narasimha Kurumanchi, which actually is made for cracking the coding interview and all these things, but this also provides a nice explanation over this particular asymptotic bounds, which you must also check out, right? Okay. Apart from that, how the questions can actually arise, you must always and always remember the particular series of the functions, right? Okay. What is this series, right? Where the square root lies, where the log lies, right? Where the log function lies, where the n square type function lies, where the say this sort of function lies, where n factorial this sort of function lies, where n to the power n sort of function lies, where 1 means constant time complexity lies, right? So you must actually remember this. Whenever you are actually getting confused in the exam that whether this function will be actually larger or whether this one, just simply put some values. For example, my students face a lot of problems while actually comparing these two functions, right? For example, we can always compare this one by putting some number. So let's take this function to be log base 2n, right? And this is the square root, right? So let's say we have 64, right? So 8 into 8 is 64. So square root of 64 will become 8, right? Now let me actually just keep it into the log 2n, right? So it will become log base 2 64. 64 is nothing but 2 to the power 6, and then log base 2 to the power 6 will become 6. So here in the square root we are actually getting 8, but in the log we are actually getting 6. You got your answer, right? The log will actually come forward, log base 2n, and the square root will be actually coming out here, right? Square root of n, something like this, right? Either you do this or you write square root, nothing, right? So it will actually come first and it will actually come later, right? And before than that, what will you have is actually 1. So square root is lesser than n, right? So that's why it's actually even lesser than linear time complexity. It is also lesser than linear time complexity, right? After this all stuff, you will get n, big O of n, right? That's actually linear time complexity, right? And after this particular one, right, you will actually get, see, one more major thing is that whether it is n by 2, right, or whether it is n, 2n, or 3n, or 4n, right, or 5n, or say 1 million n, it's still linear time complexity because there's a constant multiple of n. So you must always look at the function which are in respect to n. You must just remove all the constants, right? What this constant will do is actually just increase the particular c naught value, which is after which this particular function will hold true. I will actually take another class regarding time complexity, right? Just put a comment below if you want one, right? Which will actually explain all the depth details with how time complexity analysis is done, what are the total bounds, what is average, what is just omega, big omega, and whatever you are actually demanding. So we'll actually cover all those, but for now, just consider that, okay, if you actually the upper bound, right, for a particular function, right, let me actually guess that, okay, my worst time will be not more than this one after this particular value of n. That's what we actually say when we say big O of notation. Okay, so as I said, 1 million n will be still big O of n because that's just some constantly multiplied with n. And n by 2 is also big O of n because 1 by 2 is actually getting multiplied with n. That's the same with the now there comes n square and cube time complexity, and as we have already said, n square will actually come first, then n cube, right? Because yeah, square quadratic will actually grow very less in comparison to cubic, because if you actually try to draw a graph of the number of inputs and the particular time complexity, then you will get n not exactly these sort of graphs, but just to give you an idea. So you have even larger than that, faster you will say in comparison to other ones. So these are still polynomials, right? These are still polynomial type complexity. Some of functions you will actually get is of 2 to the power n or 3 to the power n. Now this comes to the exponential type complexity. Right? You might also get e to the power n, right? So e is nothing but we actually take 2 plus 1 comma n to the power n, right? So this is similar to this one, right? So that's what we call the exponential type complexity, e to the power n. So basically these sort of functions goes way too faster, right? Way too faster. One of such example is Fibonacci series. What happens in Fibonacci series is that you actually calculate the 4, which actually depends on 3 and 2, is 3 depends on 2 and 1, is 2 depends on 1 and 0, right? And then is 2 depends on 1 and 0, right? So what happens is that your one particular function is depending on 2. So it's actually creating 2 such forms. The next one is actually creating 2 plus another form. So it's actually increasing in the power of 2. Just see, it's actually 2 to the power 0, this is 2 to the power 1, and it's actually 2. This is 1, 2, 3, 4. 4 such forms. This is 2 to the power 2 equals 4. So your function is going to be 1, 2, and 4. Because actually 2 to the power n times something. Something like that is actually there. You can also make another function which is also having 2 to the power n times or functionality and time complexity. Okay. Similarly, if you are 3 divided into 3, right? Something like this. Something like this. Something like this. Right? Then this will be 3 to the power n. And similarly, if you actually just divide into 4, then it will be 4 to the power n time complexity. This is how your exponential time complexity goes, and you can already get this will be a lot more than 6n per time complexity, right? Right? Okay. Then you have more such time complexities like n factorial and also n to the power n. It is very, very easy. It's true. These two time complexities, n to the power n and n factorial come as an abbreviated system. The n case plus problem is no problem. This is actually going to be the time complexity. This is very, very easy. That's why they actually go to the graph of n and n graph problem, which are very unsolvable in reasonable amount of time. That's why solutions are actually also demanded in the current era to be required for these sort of problems. That is the result of NP and how and so this is also something that is here and also in this also then we also discuss a little bit of also. So during all this time complexity stuff, right? Yeah. So remaining this off. Right. Now what happens is that okay. So you will also need to learn some of the paradigms, right? With how the divide and conquer algorithm would look like. For example, I asked you that on which principle merge sort actually works, on which principle say quick sort actually works, right? Okay, so what you are actually doing in that particular thing is that in the merge sort, you are dividing the whole thing up into smaller pieces, right? And then you are merging simple pieces, then you are conquering up to the large one. So using divide and conquer in the merge sort. Similar is the case for the quick sort also, right? So you must learn the paradigm for different algorithms and learn one such example of each, that how this is actually working and why this actually paradigm is actually called this one, right? Dynamic programming is also a pretty famous question, right? Have any of you actually seen the matrix multiplication version, right? That's one famous example of dynamic programming, which is usually asked in the GATE and other exams, right? You might be actually given a matrix, right, of the say matrix chain multiplication. What the problem statement says is that say you have say one matrix of say 2 cross 3, right? One matrix of 3 cross 4 and another matrix of say 4 cross 5, something like this. So the question is that whether to multiply these two first or these two first to actually have the least number of multiplication. That's a problem, because there is no problem if you multiply these two first, that will actually become 2 cross 4, and that's actually 4 cross 5, so that will be actually 4 cross 5. So now you can actually multiply these to actually get 2 cross 5. If you actually multiply these two first, then you will actually get 3 cross 5, and then you actually multiply 2 cross 3 here to actually again get 2 cross 5. The thing is that how to order your brackets to actually have the least number of multiplications. How to get the number of multiplication is that you have, if you have say 2 cross 3 and 3 cross 5, so your total number of multiplications here would be 2 cross 3 cross 5. That's actually 2, 3, 6, 6, 5, 30. So 30 multiplications would be there. So you actually formulate a particular kind of say table in which you actually arrange particular dimension calculations that how much multiplications are out there, and actually keep on multiplying and go to top. That's actually the minimum number of multiplications. Just head out to our internet and focus on this problem. This practice one, you will get to know how to actually solve these particular or we can actually discuss that in the next class or we can require. But for this particular video set, I'm just discussing the practice questions which can actually come regarding these particular topics which we described in this video. Okay. So then we have other things like graphs reversals, like graph reversals. So now we are actually given some particular graph, right? They're given you have two solve algorithms majorly for calculating the minimum time. One is actually crystal and another is actually Prince. Right? Crystal algorithms basically like that. Just get the minimum edge without making a thing. That's it. Just get the minimum edge without making a thing. Right? You will actually given a particular graph, right? And say you have the minimum edge is here. Right? So okay, I will actually add another one, right? So what we'll do is that or I will say let me actually keep four here. So first I will actually put this particular one into my minimum time tree, right? And then I will actually go for next one. Next greater is actually so I actually choose this one, right? Okay. Next one is actually 3, right? Okay, so I will actually choose this one. Next is greater than 34. So I choose this one. If I actually connect this one, then this will be a second, which I will not avoid. So I must not choose this one, and my minimum time tree will actually become something like this. That's actually having 1, 2, and 3, and having the cost of 2 plus 1, 4, 5, 6. That's actually having 6 costs. Prince also works in a similar fashion, but it's a different pattern. Right? You actually create connected components. You actually start from a particular vertex, right? Which is actually having the least value because you want. You start with a particular vertex, and you actually keep on the track that whether which of the edge is actually a minimum one. In the classical, you are not having any consideration about any of such connected components. You are choosing randomly whatever the minimum edge was there. But in the Prince algorithm, you will actually keep in mind that which of the connected components is actually having the least edge, right? And also you will actually keep on extending further. So that's actually the idea of Prince. Just random simple example you will use the algorithms and you will actually be able to go. One pretty famous question which actually comes into exam regarding these algorithms, especially CRISPR, is that run the MSC algorithm and find that what are the total possible MSCs out there. Sometimes in a graph you actually given some sort of questions like this, that you have 3 here, 3 here, 3 here, right? So apart from that, all the values will be connected, and that will be actually connecting 1, 2, 1, 2, something like that actually. So you will be actually choosing these all first. Obviously these are minimum ones, right? But you will be actually in that one, so that you will choose this one, or this one, or this one, right? Because if you choose any of these, you will be actually having the same cost because of having 3 to 3 values. So you have total 3 MSCs possible. That's the logic we follow in many of the questions which I've seen, and also my students have just a lot sort of these sort of questions that how many minutes can 3 are possible. Another pretty famous question which actually comes from this particular concept is that what they actually just blank out the possible value of this particular edges, right? Right? And then they will ask that what should be the possible value or maximum value of this particular edge to be included in the minimum time, right? So just consider to be always including in the MST, right? So just see, have a logic that if you are trying to include other things, right? If you are trying to include other things, then what is the condition that you will always include this? That's the thing is that you must have a value which is minimum or smaller than the other values out there, which is connecting this component to this component, right? So if you have no other choice, then only you will actually include this particular edge, right? For example, other edge values will be 2, 3, and if you have say 1 edge, you will obviously include this edge here, right? As you were including in the MSC, you will start by the CRISPR algorithm. So the thing is that you must choose a particular value. For example, if I say put 5 and 6 here, then I can choose the maximum value of say 4 here, right? So that is always being included in the MSC. I will not be choosing 5 or 6, I will be choosing 4 to actually connect this component to this one, right? That's how you must actually think of the questions, and that's how you must actually solve. So go with the logic and you will be able to do that. Okay. Then we have names that we sort of yes, we have hashing. Hashing is also very much famous question for these gate guys because it takes time to actually calculate that which position will be a particular element, right? You will be actually given a series of numbers, and then you will be asked at which position this 7 will be there. They will ask a question like this one. They will give hash function which might be double hash functions also. That you will be actually calculating the hash value like h1, on different hash values. Sometimes they also give questions like I value. Don't get confused when they use I. I usually refers to the number of conditions, right? So, for example, you apply h1 of x and you get a particular value and you see a collision at there. Means already some value is there. So the I counter actually increases that, right? And it becomes 1. So the function actually becomes, for example, say 5x plus I into say 10, something like that, in this function. So for the first iteration it will be 0, let's say, or you can put in on this. Then in the second iteration it becomes 1 and multiply by 10, right? And then whole thing more 10 because the 10 is your array, right? So this will keep on increasing and it will give you different hash value of the location in which your value must lie in. So this is how you figure out what will be the particular value, and you will actually get some particular place at which your value will be residing in after resolving to say separate chaining or probing. These are two particular ways in which the hashing is actually resolved. If you are pretty much confused what I'm saying and what actually I'm referring to, just put down a comment and I will actually get to the detailed video of how hashing is done and how it's actually performed, how to do it fast in the exams like this one. Okay. Going further, we have theory of computations, right? So what questions could actually come in the theory of computation, right? Especially it's actually revolving around the regular expressions and finite automata only. You might be given a particular, say, regular expression. You might be actually given, say, a plus or say b star, something like that, or say a star, b star, right? Or you might be actually given some sort of, say, other expression like a, b, n, right? So then you might be actually asked that, okay, whether this particular expression or so whether this particular expression which they are referring to is actually a regular expression or whether it actually comes from context-free grammar or context-sensitive language, or they will be actually asking the language, right? So the thing is that you can't actually compare these things with regular expressions, right? Just simple regular expressions is actually very, very difficult, right? To actually compare whether the number of a's is actually equal to number of b's, right? So that's where we actually use different sort of languages or grammars, like context-free grammars, right? To brief, regular expression actually the model which is associated with them is actually finite automata, right? The model which is actually, or the machine which is associated with the context-free grammars is say push-down automata, in which you have one stack. You just keep on pushing the A right in the stack, and wherever B comes, you keep on popping the elements. If nothing is available out there, then it means the number of A's are actually equal to the number of B's. If the number of A's were more, then on pushing all of the A's according to the number of B's, some of the A's will be left. So that's the logic which you use with the stacks. Similar is the case when B are larger, right? You will be actually trying to pop out something, but nothing will be there. Then it means B are large, so A and B are not equal. That's how you can actually use a stack to compare these two, and that's only possible when you have some structure like a stack with you, and that's possible with push-down automata, and that's why your language will become context-free language, right? And for context-sensitive language, which are actually not mentioned here, right? Otherwise, you must know them, that when the things comes like A, N, B, N, C, M, something like that, the third entity also comes, which must be different from that. So only one stack can't handle these things, right? So context-sensitive language, or I must say a linear bound automata, is actually there with these sort of languages, right? And then at the last, you actually come out with Turing machines, right? For these and undecidability problems, that okay, so they will be actually giving you some sort of problems whether a particular problem is undecidable or not. One pretty famous example is the halting problem, right? I must say. Okay, so I will actually give you a particular exam. Let me actually give you a particular exam, a particular program, like say while let's say true, and then in this particular loop I am doing nothing. So my program will run. It will keep on running, keep on running, keep on running. Do you know whether it will actually stop or not? Do you know that? If I say, if say random is less than 0.5, then you actually do exit, right? Okay, so if random number actually comes out to be say less than 0.5 to 0.1, is it really probable that this number will actually come? It might be possible, it might never come. So this program will never halt. So you can't tell for a particular program that whether it will halt or whether it will not halt. So that's a famous halting problem, and that's actually undecidable, right? Similar is the case for different set of problems, right, which you will actually encounter. Just go for jigs or different books which you actually refer to the theory of computations, right? That there you will actually get to see a lot of examples of undecidability and similar sort of problems. Okay, then you have pretty much everything up covered, right? In this, a pumping lemma is also one which is actually in their eyes to give you the questions for the same, whether a particular expressions can be actually represented in the form of rules which are defined by pumping lemma, whether a language can be pumped in the form of itself by using the particular expression. So you just need to know the format in which the language need to be pumped, X, Y, and Z format, and then you will be able to do most of the questions which can actually come to exam. Compiler design. So you need to know what lexical analysis is, what parsing is, how to actually generate the parse tree, how to actually go for ambiguity. That's a pretty famous question which actually comes in the NET and GRF and also GATE exams, right? The ambiguity question, right? Whether a particular language is ambiguous, whether it is left recursive, whether it is right recursive, something like that. Then you have the syntax directed translation, runtime environments, intermediate code generation, doctor optimization, data flow analysis, constant propagation, Leibniz analysis, common sub-expression elimination, right? These are all the topics. So from these, most of the questions actually comes from my experience. Most of the questions comes from these parsing, right? They will be actually giving you a particular grammar, right? They will be actually giving you a particular set of grammars, like say S goes to A goes to B, C, something like that, right? You will be actually asked. You might be asked to calculate the first of a particular word, right? First of the particular grammar. You might be asked to calculate the follow of the grammar, right? So first generally refers to the particular first letter non-terminal which can actually happen, and the follow actually refers to the on the right hand side what could actually comes after a particular non-terminal. For example, if I have say A, then the follow of A will be actually small a, something like that. And if I don't have A, then I have B, then I will see that where B is actually leading me to. For example, say small b, so my follow of A will actually become B. Again, it's actually on the abstract level, just I'm actually explaining or making reminding you if you have read first and follow. If you have not, just comment me down so that I can actually come up with a new and detailed video. Why I'm actually doing this is because I will actually come for only for those topics on which the videos are required and on which the detailed explanation is required. Otherwise, if all of you guys already know that, then this would be not beneficial to come up with a long detailed video of the same which is not required. Okay, so going further, okay, one more thing is that while learning these all concepts in the theory of computation, you must always remember one example of each of such of problems, right, of each of such languages, that what could be the possible example of such language, right? And then you will actually realize and relate the properties of each of those language with whatever you have learned of the properties. Okay. Okay, so then you have all these things. Okay, lexical analysis, already is actually the one in which you actually generate the tokens based on the regular expressions. If you have actually made a compiler or just made a pseudo compiler itself in your practicals, right? So you know that how we do that, we do with lex, and then there was a program, if you remember, yak, right? So lexical analyzer actually use the regular expression and then generate one particular token, whether it is a literal, whether it is a keyword, which you write the program for. The yak is actually a parser, which actually formats or parses the particular tokens in the form of say some particular expression, that whether it is form of A goes to A plus B minus B divided by multiply by, that's all rules you define your language to process, right, or your code to process, right? So these are the stages of compilers in which the compiler actually works. First, the lexical analyzer is there, then you have the parsing, right, then you have other sort of analysis, optimization, symbol table and all. After that, your code optimization comes, and after that intermediate code is actually generated, right, and then you have the target code generation and all. So there are all steps of compiler design. So you must actually go for some resource like GFG element and then just refer to all those particular set of stages of the compiler design which actually happens out there in the stage of the compilation of the program. Okay, so these are the topics which actually comes from compiler design. Then we have the operating system, which could actually comes system call. Open is actually pretty much famous system call which actually comes out there. They again and again ask for open and its variants, right? And the system calls, other system calls which are pretty famous are fork. What it is actually being used for is actually forking a sub process from a process from your process. That's actually you create a child process from your parent process, right? So questions usually comes like if you have called fork three times, then how many child process will be created? That will be actually 2 to the power something, 2 to the power n. How many fork you have created? So 2 to the power 3 sort of processes will be actually created in total when you have actually called fork three times, right? And they might also ask that what is the return value which actually you get after calling a fork. So you must know the rules, whether if it's actually a -1, then what it is it a failure, what happens with 0, whether it is the parent process itself which was calling the fork, or whether it is a child process, right? With the child there will be a new number which will be the id of the child process which is actually created. So you must remember the rules and also guess the number of times or number of processes which will be created on calling the fork n number of times. That's the logic which you must remember while learning the system calls in itself. There are other system calls itself also, like one of the pretty famous and beloved system call is actually exec system call, execute a new process. So they might ask you that whether exec system call with ls what it does. So what you will do is actually just list your directory, and there will be a syntax of your this exec system call, and different variants like exec v and exec vp and all such variants. They will ask that whether which of the variants are actually correct and which is not. So these all sort of questions are also pretty famous in the gate examination. And then they will provide the path like bin/sh, and then they will actually give you a command like ls, right? Okay, so your current process which is running will be replaced with this execute system call, right? And then you will be asked that what it will do and what it will perform. So just by looking at exec and the ls statement, you will see, okay, so these both will actually just list my directory and give the output to somewhere and redirect the output towards somewhere. So you will actually do in such fashion. Okay, so then you have threads and processes. So they will ask you the difference between threads and process, that what is actually being separated in threads, whether they have the same memory, whether they have the same stack, or whether they have different stack. What is common in between all the threads, what is common in the process, and then are there different. So the thing is that process is a bigger entity, thread is a small entity. In the same program you have multiple threads, but you have different running processes. If you are creating new processes, they will have their code segment, data segment, right? But the threads actually share the code and their data segment, but they have different stacks to execute, so that you have different recursive function could be called into different threads, right? Okay, then they have inter-process communication. Recently they have started asking a lot of questions from inter-process communications also, right? Like what are the methods of inter-process communication? How do the process communicate? One such example is actually message box. Recently they have been asking questions from message box that how the how a process one works, and process A and process B will communicate by using the message boxes, right? How will you actually create the connection? How will you actually establish a connection? How will you transfer the data? What will be the signal of transferring the data? How will it actually end? Others are actually pipes. Other such mechanisms also include shared memory. So you need to learn all those concepts in this particular scenario. Concurrency, synchronization, deadlock, right? CPU and IO scheduling, memory management, virtual memory file systems. So the thing is that right, so you are actually asked you are usually asked questions about deadlock in this particular subsection, that what are the 4 possible conditions of deadlock. You already know, you must remember that there is a cycle, right? Wait for cycle, that you are holding some resource and then you are actually waiting for some other resource, and this forms a particular cycle in which you are stuck, then nobody is able to release that particular resource so that other can use it, and that forms a deadlock. Then other one is actually wait for, means you are holding one particular resource and waiting for another resource for a particular entity, right? And there is no preemption, that you can't forcingly take out a resource from one particular entity, right? And there are limited number of resources. That is, you can't have infinite instances of each resource. You can't have infinite printing jobs to be given to the printer. You can't have infinite outputs, right? So only one instance is there which you need, right? And any process could actually need, right, in a particular point of time, right? So these are the conditions which must hold for the deadlock. And one such famous algorithm which is used to resolve deadlock is actually Banker's algorithm, right? So you must remember these concepts and a little bit about Banker's algorithm, how it actually works, right? See, if you have the power to take out the resource forcingly from a particular process, then deadlock would not be there, right? They might also ask you questions that how to resolve deadlock. What are the strategies when a deadlock happens? There are strategies like you avoid the deadlock, you ignore the deadlock, right? You prevent the deadlock and you resolve the deadlock. There are some strategies which you actually need to study about in the deadlock handling, but it's a pretty famous question which actually comes again and again in the gate examinations. Then there comes memory enablement, virtual memory. Virtual memory is also pretty famous, right? That's it. How you increase the memory, right, in the operating system. And also relating to this particular concept, you have things like paging, you have segmentation. This all comes under the memory management, right? How you manage a particular memory, how to divide the memory. So in the segmentation, we have different sizes of section according to, this is actually kind of say user point of view, code, data, and other sections, right? Like there are different sizes, varying sizes, right? But in the paging, you have say fixed size partitioning, right? Internal fragmentation happens in this one because if you fill this much of space, only this much of left. But the external fragmentation happens in this one because when this actually is removed, a block is actually happening around here, another block might be happening around there. You have total block which is larger than the request, right? But that's actually being spreaded around there, so you can't actually allocate that. And external fragmentation is more severe than internal fragmentation. I'm just making you remember all the concepts which you might have already learned. So these all things actually happen in the paging and the paging and the segmentation things, internal and external. So questions are asked on the fragmentation also a lot. How the file systems are actually managed in the Unix operating system, this is also asked. They might ask you about what inode is, right? What is a super block? What is a boot block? They might ask you how the linked list is actually managed. What is the directory, right? So of all the files which are actually out there, how the blocks are actually managed, where the super blocks is actually saved. So these are questions which you must actually point or note down now. So and you must try finding out the answer of each of those, and you actually cover most of the concepts which are around there in the file management. While coming to the databases, right? What can actually be possibly asked? Let me actually just review in a bit of detail. So the thing is that in the databases, they have ER modeling, right? They might ask you that what this thing is representing in the ER entity relationship model. What a dotted entity is actually representing, right? They might ask you. This is what I'm telling you is actually pretty frequent questions, right, which have came already in the gate examinations till yet, and also UGC net examination for if you are preparing for JRF. They might be asking you what our rhombus is actually representing, how the entity is actually getting represented, how the attributes are getting represented, how multi-valued attributes are represented, how composite attributes are getting represented. So most of the questions actually come from the representation because people used to confuse a lot, right? Say somebody ask that a particular attribute with the underline actually represents what? That's a primary key. So you must remember these concepts. These are again and again repeating in the gate level examinations and UGC net examinations, right? Then you might be asked questions about relation algebra, right? Okay, so they might ask you to select the option which is correctly representing a particular query, right? They will give you a SQL query and they will ask that which of the following relation algebra correctly represents the formulation for a particular query. So you will have the projection operation, right? You will have the selection operation. Selection is actually equivalent to SELECT. That's actually selecting a particular column, right, from a particular selection of rows, right? So you have a particular table being selected. Then now you are actually only choosing some sort of column, so you will actually use a pie. That's actually projection. for choosing based on the particular value, you will have this selection operator, right? And then you have also called joins, right? Joins based on some particular condition, right? So you will represent the joins with this particular symbol, right? And you will actually represent the particular joining criteria here, that this equals to this, something like that. So let's actually have a look at a bit of the relational algebra, because they are again and again repeated in the gate level examinations, and also UGC in whatever whatever university level examination you are actually giving out. Okay, then you have the SQL, basic SQL statements. You must okay, so in this particular one you must refer to exists a lot. Exists is a little bit complex if you actually want to get handy with this particular one. It's actually kind of the thing, your outer loop runs first and then your inner loop runs. Like for each of the outer loop, your inner loop runs, and for this inner loop you match the things with the outer one, and then you reject or select some of those particular tuples. That's the basic idea of this exists. In the similar fashion, we have not exists, right? It's actually just the reverse of those, where something like a given criteria is not existing into your table which you are specifying in your inner query. So you actually specify those. You must know the in operator, you must know the aggregate operator, like average, how the average works, how the count works, right? How the min works, how the max works, right? So that will be all based on the group by commands, which groups the rows which are having similar value but having the different value on other columns which are being joined. Integrity constraints, right? You must know about the primary key constraint, you must know about the referential key constraint, you must know about the check, right? Check constraint, domain integrity constraints, right? And most importantly, you must know about normal forms. So let me actually brief you up a bit about normal forms. If you want a detailed explanation, I can actually come out with a video, as I've already explained. So 1NF is a normal form in which you don't have multi-valued attribute, like you don't have these a comma b attributes. If you have so, then you will actually make two such rows in which one will actually contain A, one will actually contain B. Two such rows will actually there. So this will actually be called 1NF, this won't be. Now the 2NF is the condition in which you have no partial dependency, right? For example, you have say AB to be the primary key of a particular table, and that might be defining C. So there must not be any dependency in this one, that is actually like B goes to C, because the C is partially depending on this B. So what you need to do is that you need to make another table of BC to resolve this 2NF dependency, to make it a 2NF table now, right? So you will be only left with AB, and B might be referring to this one, and B to C is actually another table. So that's how you will actually just split these particular tables one to make it into 2NF. Now you have 3NF, in which you must not have transitive dependencies. That is, if A goes to B and then then you have the B goes to C, then A is indirectly determining the C. That's not allowed in 3NF, right? Only direct relationships must be there, like A goes to B and A goes to C, something like that. There must not be anything like B goes to C. If it is there, then A is reaching C through a non-prime attribute, right? So that's how you actually get it, and that's how you resolve it, whether a particular relation is forming 3NF or not. Then you have the BSCNF. If you will be actually given a question in which you have two particular columns, right? This already in BCNF without thinking anything, right? That's a shortcut which you actually can use in an examination, right? Any table with the two columns is always in BCNF, right? Okay. Other thing is that all the determining attribute must be a prime attribute. That's another rule of this BCNF, right? That's actually a stricter form of 3NF, right? So that's also another criteria which you need to check, right? For a particular table, there might be questions, right? And usually they don't ask the questions from 4NF and 5NF because they actually go into the advanced. But yes, till BCNF they ask very oftenly, right, into the examinations. Okay, so then you have the file organization, how the file is actually there. Then you have the indexing, how the indexing is done, why indexing is done. So from the name itself, you can actually guess to increase the performance, to actually fasten up the performance, the indexing is actually done. Then the most important is actually transactions and concurrency control. you will be asked different schedules, like this process follows this one, this process follows this one, this process follows this one, something like that. And then you will be asked, okay, whether this particular schedule will create some problems, right? Whether a particular problem process will actually be facing different problems, like reading wrongly or might be writing wrongly, something like that. So you will be actually given schedules like read of A, write of B, something like that, and after that commit and the rollback. You will be asked that which process needs to be rolled back if a particular system is actually crashed. So something like that questions you might actually practice in this transition concurrency control, which are asked again and again into gate level examinations. Now you have the computer networks, right? So you have the computer in the computer networks, a lot of questions are actually getting asked, right? In the OSI, you must learn at least one application of each of the layer, right? So you have those 7 layer of OSI standards: application, presentation, session, then you have the transport, then you have the network, then you have the data link, then you have the physical. So these all are the particular layers of the OSI model. Similarly, you must know the TCP/IP model also, in which the application, presentation, and session are combined into application only, and then you have the other set of layers, right? Like you have the transport, then you have the internet layer, and then you have the other sort of layers which are below there. So in the TCP/IP you have 5 layers, and in the OSI you have the 7 such layers out there. And there's a bit difference between these two architectures. In the reality, TCP/IP is actually being followed because it's easy to implement, but in the conceptual level, to actually divide the concerns among the different levels, the OSI is actually being used. Then you have the protocol stacks, which protocol actually works on which layer. For example, if I actually ask you an application level, or if I ask you that SMTP works on which layer, then it actually works on the application layer. If I ask you that IP works on which layer, then you must have in mind that it actually works on the network layer. If I ask you different set of protocol, right, like a telnet, that's actually on the application layer. Presentation will be always dealing with the encryption, compression, and decompression, formatting, something like that. All are actually performed on the presentation layer. So SSL actually works there, right? And then we have the session layer, which actually deals with the session initiation and maintenance, right, over a long period of time. The transport layer actually works on the end-to-end delivery. This question is also asked again and again, that what is end-to-end delivery, which layer actually works on port-to-port delivery, something like that. So the answer is always transport, right? What is port? So on a system, the process is running on, say, 8080, let's assume, and on another system, let's say, it's working on 8081, right? So your data will actually come from this particular port and must go towards this port. So your process must ensure that the data reaches the right port after it reaches the destination station, right? So this is actually called the port-to-port delivery. TCP actually follows the TCP TCP protocol, right? And also UDP works on this particular transport layer, transmission control protocol, and user data protocol. UDP is actually faster because it isn't reliable. You actually send the data, you don't know whether it is received by the receiver. But if you want to make sure that it is received by the receiver, then you must actually use the TCP protocol instead of UDP. TCP protocol is actually used in where you actually use like other protocol on the top of other protocols like FTP for the session initiation and all, right? You actually use TCP where you have to shortly transfer a particular data, and in the protocols like real-time gaming, like you might be playing PUBG, right? In those, and also live streaming of the YouTube channel, then they use UDP because you want it to be fast. And you might also notice sometimes while playing PUBG, you actually miss some of those frames of the game and other games out there, right? You might skip some frames because it's not re-sending that particular frames, right? And it's not retransmitting those. That's why it's actually using UDP. Another example is DNS, which is actually using the UDP protocol because you just want to first send. What does DNS does? Let me tell you. You actually know google.com. google.com, but you don't know the IP address, you can't remember that IP address. So what you will do is actually just send the google.com towards a server, right, DNS server, domain server, and then it will actually return you the particular IP address 104 or 105 something IP address that you will work upon, that your browser will work upon hiddenly, right? So for example, if you know this particular IP address, then you actually just do one experiment, go to your browser and then type the particular IP address, and that will still takes you towards google.com, right, that particular page of Google. Why? Because the browser didn't need it to convert this google.com into this particular IP address, because you have done it for it. But internally it does is this conversion. That's actually why domain name service is one, and you don't want it to be slow, you want it to be fast. That's why you're actually using UDP. Okay, then you have the packet circuit and virtual circuit switching. Now you have the switching techniques. In the packet switching, you have a particular another one was also there, message switching. There's a bit of difference. So the thing is that in the packet switching, your data is divided into multiple packets. They route from different paths and then reorder at the destination. That's how you actually reach. Then you have the circuit switching, in which you have a circuit or bandwidth stabilized, like while you call or call some of your friend, then the line actually comes like B. What it's actually doing behind the scenes is actually setting up all the pathway towards your all call will be diverted, right? So while setting that particular path, is actually using the circuit switching behind the scenes, right? So it's setting up the particular path, and through that particular path your data will go. So it will take time, and it will reserve the particular bandwidth as the fallback of this particular technique, and that will be asked in the gate question, that what is the fallback of circuit switching, what is the fallback of packet switching. So you must know this. Data link layer, framing. What is framing? Just making the frames by the data link layer. Error detection. How do error is detected? One such algorithm is CRC, cycle redundancy check, which actually detects the error, and how to correct the error. So Hamming code is actually there. Medium access control layer, which actually works on the MAC sub layer, right, which is working on the different principles, like using the MAC address, right. And then we have the Ethernet bridging routing protocols, right? Okay, which are the routing protocols which you actually use? Shortest path, flooding, distance vector routing. Distance vector is again asked that which algorithm is actually being used in the distance vector routing. That's actually the Bellman fold algorithm, and which algorithm is actually used in the different algorithm. This link set routing. These are all questions actually come to you, right? So link set routing is actually using this algorithm, and distance vector routing is actually using the Bellman fold algorithm. You'll be asked to match these things up into a sort of say table. That's actually what is being asked in the gate level questions, to make it a little bit hard. Now you have the fragmentation and IP addressing. How do a CIDR notation actually works? Classless classful inter-domain routing, and then you have the classless addressing, right? So basically you have also questions from the subnetting, that how the subnetting is being performed, what is the address of the subnet, what is the how many hosts are there which are actually available out there to be configured and to be used. So these are the things up. And then you have you will be asked about the ERP address resolution protocol, dynamic host configuration protocol, internal control message protocol. What it does, it actually